boy throws a ball at a target. At the instant when the ball leaves the boy's hand at the point A, the ball is 2 meters above horizontal ground and is moving with speed u at an angle alpha above the horizontal. In the subsequent motion, the highest point reached by the ball is 3 meters above the ground. The target is modelled as being the point T, as shown in figure 4. The ball is modelled as a particle moving freely under gravity. Using the model, part A asks us to show that u squared is equal to 2g divided by sine squared alpha. Now, the first thing we want to do on this question is consider the speed, because we've been given this speed to be acting at an angle above the horizontal. And the problem with this is in calculations like this, we tend to need to resolve vertically and horizontally. We don't normally resolve at this random angle alpha, just because it isn't really convenient with everything else. And so for our calculation, if we need to resolve vertically or horizontally, we need to find a way that we can speak about the speed in these terms. And the way we can do that is we can resolve vertically and horizontally. So if we first resolve vertically upwards, we can see that we have this right angled triangle here, where this is the opposite of this angle, and this is the hypotenuse. And we know that opposite and hypotenuse means we need to use the sine rule, and so that we can say that this vertical component is equal to u sine of alpha, because it's like if we had sine alpha is equal to opposite over u, so we times both sides by u to get this equation for the opposite. And if we do the exact same thing horizontally, acting in this direction, we have an adjacent and a hypotenuse, so this ends up being equal to u cos of alpha. And so now that we have our speed resolved vertically and horizontally, it should make calculations much easier. And the other thing that we can mark on this diagram, using the information we've been given, is the fact that we're told that the ball's modelled as a particle moving freely under gravity. And what this actually tells us is that the acceleration, when we resolve vertically downwards, the acceleration is the gravitational acceleration, which we can call g. And this is the only acceleration that acts on the ball. So if we mark this on, that the acting downwards, and we know it's acting downwards just because gravity acts downwards, so that's the way that this acceleration acts, that we have this downwards acceleration of g meters per second squared. And this is all the information that we can currently mark on the diagram that we haven't already been given. So now, if we look back to our actual question of what we need to show, this expression here, we can see that to get this, first of all, we will need to use one of the constant acceleration formula. And the way we know this is partially because this is a projectile motion question and they do tend to use these Surratt equations. But also, we've been given this speed, we have these distances above the ground that we could use as displacement, and we have this acceleration. So all of these are things that we would use in these equations, and so these are all kind of hints about what we should be doing. But what we don't know with these equations is whether we should resolve vertically or horizontally, because either would be valid, but which one would get us this exact expression? And the way we know that is if we look at this expression, we can see that we have a g, and we can see we also have a g here in our acceleration that acts vertically downwards. And we can see that we also have a sine alpha, which appears when we resolve vertically for our speed. So these both occur when we resolve vertically. So to get them in our equation, we're going to need to construct a Surratt equation where we resolve vertically upwards, just because upwards is the direction that the ball moves. So first of all, we have s, and our displacement here, if we form a Surratt equation between A and this highest point here, just because these are the 2 points we know the most about currently, we know that our displacement from here to here must be 1 meter, because we've gone up from 2 meters above the ground to 3 meters above the ground. So the displacement of that is 3 take away 2, which is 1. And now our initial velocity is this velocity at the point A when we resolve vertically, which we previously wrote out to be equal to u sine of alpha. And v is the velocity at this point here, the highest point. And although we've not been told this in the question, a general assumption we can make about the velocity at the highest point of projectile motion is that we can say it's equal to 0 meters per second. This is just kind of an assumption we make. And next we have the acceleration of the ball, and as we stated previously, when we resolve vertically downwards, the acceleration of the ball is g meters per second squared, which means if we resolve vertically upwards, it must be the opposite of this, which would be negative g. We're acting in the opposite direction that the acceleration acts. And lastly, we have t, and we don't actually know what the time is, but we also don't need to know. We have enough information here, as well as the fact we can see in this final expression, there has nothing to do with t, time. So we can see that it's not going to be in our end result, and so we don't need to know it. So now, if we think of the 5 constant acceleration formula, which one has all of these but t, time, then the equation we need to use is v squared is equal to u squared plus 2as. So if we substitute in these terms that we have, 0 squared is just 0, and then we have u sine alpha squared plus 2 multiplied by minus g multiplied by 1. So if we expand out these brackets we have on the right hand side, u sine alpha all squared is the same as u squared sine squared alpha, because we have to square both terms, and then 2 times by minus g times by 1 is just minus 2g. So now if we want to rearrange this in the format we've been given in this question, we need u squared by itself. So if we add 2g to both sides and divide by sine squared alpha, that's what we'll end up with. We'll have u squared is equal to 2g divided by sine squared alpha, which is exactly the form that we want to give in the question. And now this question is worth 2 marks, and our first mark actually is a method mark, and it comes from resolving vertically, which we've done here. And our second mark is an answer mark, and it comes from ending up with what we've actually been given in the question. So getting the right answer in the end is our second mark. The point T is at a horizontal distance of 20 metres from A and is at a height of 0.75 metres above the ground. The ball reaches T without hitting the ground. Part B asks us to find the size of the angle alpha. So first of all, if we just mark on the information we've been given to the diagram, we know that this distance from T to the ground is 0.75 metres and this distance from A to T is 20 metres. Now, the first thing to note is we can't just find the angle A with one Suvat equation like we did in part A. We're going to need a simultaneous equation because we just don't have enough information to simply find alpha straight away. Because you may be able to see, if we just resolve, for example, horizontally, we're going to end up with something to do with u, and that is another term that we don't know, which means we can't just find alpha. So we're going to need a simultaneous equation where we might be able to cancel out u or find u, which will therefore lead us to be able to find alpha. So if we do this, one way we can form a simultaneous equation in this kind of context is if we resolve vertically and then horizontally, we should have 2 equations with very similar terms that we should be able to equate or substitute into one another. So first of all, if we resolve vertically upwards, but now between A and T, as opposed to A and this highest point, we know that the displacement between A and T is going to be negative because we've gone down from being 2 metres above the ground to being only 0.75 metres above the ground, which means we're going to end up with a negative displacement, and that displacement is going to be negative of 2 minus 0.75 because that's the difference between this point A and this point T. So we know that our displacement in the end is minus 1.25. Now u, our initial velocity, when we resolve vertically upwards, is going to be this component here, u sine of alpha. And our final velocity, we don't know, so we've not been told anything to do with the final velocity at t, but we also don't need to know v. And the reason for that is that if we were going to make a simultaneous equation, we can say that the vertical component of our final velocity is not necessarily the same as the horizontal component of our velocity. So we wouldn't be able to equate these two v's, and that would make a simultaneous equation quite complicated. So although we don't know v, we also don't need to know v. It's better to leave it out of this equation. And now a, when we resolve vertically upwards, as we did in part A, we know is minus g. And t, although we don't know the time, we can also say that we'd like to find the time because thinking back to our simultaneous equation, we know that the time it takes to get from A to T when resolving vertically is going to be the same as when we resolve horizontally. So these are something that we could equate, and so could be helpful in our simultaneous equation. So if we say that we don't know T but would like to find T, then we need to pick the constant acceleration formula that has all of these terms but V, and that equation is S is equal to ut plus half at squared. So if we substitute in the terms, we are left with minus 1.25 is equal to u sine alpha multiplied by t plus a half multiplied by minus g multiplied by t squared. And so we can't do much with this now because we have so many unknown terms like u, alpha and t. But the one thing we can do is to just simplify a little bit by expanding out these brackets on the end. So we're left with minus g over 2 multiplied by t squared on the end. And this is as far as we can simplify it for now, which is why we need to do a simultaneous equation. So if we do the exact same thing, but now resolve horizontally, if we resolve to the right, just because that's the direction the ball's moving in our diagram, then our displacement must be 20 meters, because we know, as we're told in the question, that the point T is at a horizontal distance of 20 meters from A, so our displacement is 20. Our initial velocity when resolving horizontally is the horizontal component of u, which we found to be u cos of alpha. Final velocity we don't know, but also don't need to know for the exact same reason that we didn't use v when resolving vertically. And our acceleration, when we resolve horizontally on a projectile motion question like this, the acceleration is actually 0 meters per second squared. There's no acceleration resolving horizontally. And lastly, t, we don't know, but we'd like to know, for the same reason we did when resolving vertically, which was that this t here and this t here are exactly the same, and this could come in handy in our simultaneous equation. So again, the only equation that doesn't have v in it is the equation s is equal to ut plus half at squared. So this time, if we substitute in the values we have 20 is equal to u cos alpha multiplied by t. But this time it's plus a half times by 0 times by t squared. So anything multiplied by 0 is 0, so this is as far as we can do this equation. However, if we look at this equation here and this equation here, we can see that they both have a t in them, but we don't want t in our final answer because we're trying to find alpha. And so a good way to cancel out these t's, as well as kind of bring these two equations together, is to substitute in 1 as t. So if we rearrange this bottom equation we have here in terms of t, and so we're left with t being equal to 20 divided by u cos alpha, we can actually substitute this into our first equation. If we call this equation 1 and this equation 2, and we say that we want to substitute in 2 into 1, then we'll actually be left with something that's just in terms of u and alpha, which should help us find what alpha is. So now we're left with minus 1.25 is equal to u sine alpha multiplied by 20 over u cos alpha, and then this is take away g over 2 multiplied by 20 over u cos alpha, all squared. So now if we want to simplify this a little bit to make it less complicated, we're going to end up on the right hand side with u sine alpha times by 20 over u cos alpha. And so if we've got a u on the numerator and the denominator, these are going to cancel out. And if we have a sine alpha on the numerator and a cos alpha on the denominator, we know that by definition, sine alpha over cos alpha is equal to tan alpha. So this first two brackets multiplied by each other will actually simplify down to 20 tan of alpha. And now if we do the exact same thing with the second terms in this equation, if we first expand out this bracket of 20 over u cos alpha all squared, 20 squared is 400, and then this is divided by u squared cos squared alpha. And so if we now multiply this all by minus g over 2, we'll find that since we have a 400 on the numerator and a 2 on the denominator, 400 divided by 2 is 200. So we can actually simplify this now to 200g divided by u squared cos squared alpha. And so now we have this equation. Although it's simplified, we can see that we have this tan alpha and a cos squared alpha, so we can't solve for alpha just yet. But what we can do is use an equation that we had in part A for u squared, because if we substitute that in, we've now gotten rid of all the u's, which would be very helpful for finding what alpha is. And that equation, if we write in that we should substitute this in, the equation from part A was that u squared is equal to 2g divided by sine squared alpha. And we can substitute this in because we have a u squared here. So if we were to do that, we are going to end up with minus 1.25 is equal to 20 tan alpha minus 200g divided by 2g over sine squared alpha multiplied by cos squared alpha. So now we want to simplify this fraction a little bit because it's a bit complicated at the moment. We can see that on the denominator we have 2g times by cos squared alpha over sine squared alpha if we expand out those brackets, and cos squared alpha over sine squared alpha is equal to 1 over tan squared alpha, because it's kind of the inverse of sine squared alpha being over cos squared alpha. So now we end up with 200g over 2g over tan squared alpha. And we can rewrite this once again to simplify it even more so we don't have a fraction within a fraction. That this can actually be rewritten as 200g times by tan squared alpha over 2g. And then we have a 200g over 2g, which then cancels down to 100. So eventually, this fraction all cancels down to take away 100 tan squared alpha. And so you can see now that what we have resembles a quadratic equation because we have a tan squared alpha, tan alpha, and then just a number, a constant. And so if we rewrite this to look even more like a quadratic, in that it's equal to 0, if we add 100 tan squared alpha to both sides and take away 20 tan alpha, we're left with 100 tan squared alpha, take away 20 tan alpha, take away 1.25 is equal to 0. And so if we were to solve this as a quadratic equation, you can see that we would end up with something to do with tan of alpha, which will allow us to find alpha. So to solve this quadratic equation, we can go about it one of two ways. We can factorise this, as we would any quadratic equation, or we can use the quadratic formula. So if we were to go down the second route and use the quadratic formula, generally the quadratic formula is that x is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So in our context, instead of x, we have tan of alpha, and then our a is 100, our b is minus 20, and our c is minus 1.25. So if we substitute these in, minus 20 is just 20, and then it's plus or minus the square root of minus 20 squared minus 4 times by 100 times by minus 1.25. And then this is all divided by 2 multiplied by 100. So if we simplify this down a bit, more specifically what's inside this square root, we're left with tan alpha being equal to 20 plus or minus the square root of 900 divided by 200. And we can see that we're going to end up with two different values of tan alpha because we have plus or minus involved. So first of all, if we do 20 plus the square root of 900 divided by 200, we're left with tan alpha being equal to 1 over 4. And if we do tan alpha is equal to 20 minus the square root of 900 over 200, we're left with tan alpha being equal to minus 1 over 20. And so to find alpha from these, we just have to take the inverse of tan. So here, the inverse of tan of 1 over 4 is 14.0 degrees to 3 significant figures. And here, alpha is equal to minus 2.86 degrees, again, to 3 significant figures. Now the problem with this is we can only have one value of alpha, and the way we can figure out what that is if we think about this angle up here. This angle can't be negative because we can see quite clearly that it's pointing up. The ball is thrown upwards. And so this angle can't be negative. But what we can do with an angle involving tan is we can add 180 degrees on to get the next angle. So if we visualize that on a graph, it would be the next value of alpha along. And in this case, adding 180 onto minus 2.86 gives us 177 to three significant figures. But again, we can see that this angle here, alpha, needs to be between 90 degrees and 0 degrees, because if it was any more than 90 degrees, it would be pointing somewhere out here in this direction, which is away from the target T. It has to be within this. If this is 90 degrees, it has to be this or less. And so we can say that even if we were to add 180 degrees onto this, we still wouldn't get a value of alpha that makes sense in the context of this question. And so we can say, if we go back to our values of alpha, that we can discard minus 2.86 degrees as an answer, because that wouldn't make sense, and adding 180 degrees on still wouldn't make sense. And so we can conclude that the answer to our question is that alpha is equal to 14.0 degrees to three significant figures. And this question is worth 9 marks. And if we go back to the start of our workings out, the first 2 marks come from when we resolved vertically upwards. We get a method mark for just doing it, and then a further answer mark for doing it correctly and ending up with this expression here. And then we get another 2 marks for doing the exact same thing but resolving horizontally. So a method mark for doing it and an answer mark for doing it correctly. Our next mark is actually a method mark, and it comes from substituting in this equation for t into this equation 1. So doing this gets us a method mark, and then we get another method mark for substituting in this expression here for u squared. So doing that is a further method mark. And then we get an answer mark for then ending up with this quadratic in terms of tan of alpha. And then a further method mark for solving this, and you'd get a mark for doing this by factorising or by using the quadratic equation. Either are fine, but that's a method mark. And our last mark, our 9th mark, comes from ending up with this answer of 14.0 degrees for alpha. Part C is asking us to state one limitation of the model that could affect your answer to part B, our answer to part B being the value of this angle here. Now, if we think about this question in a more kind of real-life sense, then we know that this ball goes from A to T, where T is a target. And this target isn't going to be one singular point in space where the ball has to hit this exact point for it to hit the target. The target will kind of be somewhere where the ball can hit different points on it, and it still hit the target. It's not going to be one singular point. And therefore, if there's a range of kind of places that you can hit this target, then there's also going to be a range of different ways that this ball can be thrown to hit it in terms of the angle that you throw it at. So you might be able to throw it a little bit lower than what this arrow is indicating. So an angle a little bit smaller than alpha, and it might go in this direction, but it might still hit this target because the target isn't one point. And so we can say that since the target isn't a singular point, it has dimensions, that there must be a range of possible ways that we can throw this ball that will still hit the target. And so there's going to be a range of values of alpha, not just 14 degrees as we found in part B. And this is one possible answer. The mark scheme actually gives a list of different answers you can say. There isn't only one thing you can put. Something else, you could talk about the fact that in real life, there would be air resistance acting on the ball, so the angle might differ slightly, or the ball will have dimensions as well as the target, as well as the fact that the wind will have an effect on kind of the angle that the ball is thrown at and the way the ball is thrown depending on how strong the wind might be on that particular day. And these will all have an effect on the possible values of alpha. So we could also say any of these. And these are all just examples given in the mark scheme. Any valid limitation of this model that will affect the angle will get you the mark. These are all just examples. But stating any one of these, for example, this one about the dimensions of the target, will get you the 1 mark available for the question. Now, part D is asking us to find the time taken for the ball to travel from A to T. And luckily, in part B, we actually found an equation that was to find just that, involving the time taken to get from A to T when we resolved horizontally. And that equation was T is equal to 20 divided by U cos alpha. And now the problem with using this equation straight away is that although we know what alpha is, we don't yet know what U is. And so to use this equation, we need to find out what U is. And the way we can find out what U is use another equation that we found, this time one we found in part A. And that equation is the equation U squared is equal to 2G divided by sine squared alpha. Obviously, we could have found another equation in terms of U, but since we already have this one, where we know all the terms apart from U, it's just easier to use one we already have. So we know that if alpha is equal to 14.0, as we found in B, we know that U squared is equal to 2G divided by sine squared 14.0. And so if we square root this and actually solve it in a calculator, we get that U is equal to 18.3, but that's to 3 significant figures. In your calculations, use the entire value just for simplicity if we write down the first 3 significant figures. So now that we have a value for U, we can use our initial equation, and that equation was T being equal to 20 over U cos alpha, again the one we found in part B. So if we substitute in the values we know, which is U and alpha, T is equal to 20 over 18.3 cos 14.0, and if we solve this in a calculator, we find that T is equal to 1.13 seconds to 3 significant figures. And so this is the time taken to go from A to T, because that's what this original equation was measuring in the first place. And this question was worth 3 marks, and our first mark is a method mark, and it comes from finding U using our value of alpha, which is what we've done here with this equation. And our second mark was a method mark again for using this equation that we've done here and finding what T is. So using the T equals 20 over U cos alpha is our second mark. And our last mark is an answer mark, and it's for ending up with T being equal to 1.13 seconds.